System design is not just about writing code. It's about designing systems that can survive growth, scale with users, adapt to future changes, and stay maintainable years later. In today's video, we'll look at the big picture. Once you understand this, everything will start to make sense when we dive deeper into each component in future videos. Let's get started. At the highest level, we have system architecture. This is where we decide the overall shape of the system. Should everything live together inside one application? Or should we split it into multiple independent services? This is where terms like Monolith, Microservices, event-driven architecture, and serverless come in. Imagine we are building a small to medium-sized e-commerce application. Now we need to make an important decision. Should we use a monolith? In a monolith, everything lives inside one application. The product system, payment system, inventory, authentication, admin dashboard, everything together. The biggest advantage? Simpler development and deployment. One project, one deployment pipeline, easier debugging, faster development for smaller teams. But as the application grows bigger, scaling becomes less flexible. Maybe one day our payment system suddenly receives massive traffic during a sales event, but the inventory module barely gets used. In a monolith, scaling only one part independently becomes harder because everything is packaged together. Then we look at microservices. Instead of one giant application, we split the system into smaller, independent services. Payment becomes its own service. Inventory becomes another service. User authentication becomes another. Each service can scale independently, deploy independently, and even use different technologies if needed. Sounds amazing, right? But now complexity increases too. Services need to communicate over the network. We need service discovery, distributed logging, API gateways, and we must deal with network latency and partial failures. So, for many small to medium projects, starting with a well-structured monolith is actually the smarter decision. And later, if the system grows large enough, we can gradually extract certain modules into microservices when there is a real business need. But now another problem appears. Even if we choose monolith architecture, surely we should not throw everything into one giant file, right? Imagine traveling back to the early days of web development. A developer creates a single file and starts putting everything inside it. SQL queries at the top, business logic in the middle, HTML at the bottom, CSS mixed everywhere. Over time, the file grows into 20,000 lines of code. One developer changes the checkout logic and accidentally breaks the login page. Another developer edits the same file and Git conflicts explode everywhere. Nobody fully understands the system anymore because every responsibility is tangled together. This is what people call spaghetti code. And this is why we introduced architectural patterns like MVC, MVVM, clean architecture, or hexagonal architecture. After deciding the system architecture, we can decide how we are going to organize the folders and files inside the application. You can have MVC or MVVM inside a monolith architecture, or MVC or MVVM inside each service if you're using a microservices structure. Since our project is still relatively small, we choose MVC because it is simple and practical. Models handle data, views handle UI, controllers handle incoming requests and responses. But even then, we do not want massive fat controllers containing hundreds of lines of business logic. So we introduce a services folder. Payment service handles payment logic. Email service handles notifications. Now the code base becomes cleaner, easier to maintain, and much easier to migrate in the future if we ever decide to move toward microservices. Instead of extracting functionality from one terrifying 20,000 line file, our modules are already separated logically from the beginning. Once the application structure is organized, we zoom in further. Now we face smaller day-to-day engineering problems inside the system itself. For example, what if today we support PayPal, but next month we also want Stripe and another payment provider? We do not want giant if-else statements everywhere checking payment types. This is where design patterns help us. Design patterns are reusable solutions for common software problems. We have a total of 23 Gang of 4 patterns. For example, the strategy pattern allows us to swap payment methods easily. Each payment provider follows the same interface, so our checkout system does not care whether the user pays with PayPal or Stripe. And we also have some advanced design patterns like CQRS, Command Query Responsibility Segregation. Sounds complicated, but the idea is simple. Reading data and writing data often have very different needs. In our e-commerce app, customers may constantly search and browse products thousands of times per minute, while actual product updates happen far less frequently. CQRS separates read operations from write operations, so each side can be optimized differently. Not every project needs these patterns immediately, and you definitely do not need to memorize all 23 Gang of 4 patterns. In real-world projects, only a few are used again and again. The important part is understanding the problem each pattern solves. And underneath all of this, underneath the architecture, the folders, and the patterns, are the fundamental engineering principles. These are the invisible laws that keep the entire system sane. First principle, keep it simple, stupid. Developers often love over-engineering. We imagine future scalability problems that may never happen and create insanely complicated solutions for tiny projects, but complexity is expensive. A simple solution that works well is usually far more valuable than a genius architecture nobody understands. Then we have the don't repeat yourself principle. Imagine calculating tax logic in 5 different places inside the project. One day tax rules change, and now you must remember to update all 5 locations. Miss one, and bugs appear immediately. Dry encourages centralizing repeated logic into reusable components. And then we have solid principles. These principles help us write flexible, maintainable code. For example, the single responsibility principle tells us that a class should focus on one responsibility only. Our email service should send emails. It should not also process payments and generate PDFs at the same time. When responsibilities are separated cleanly, future changes become safer and easier. These principles do not tell you exactly what to build. Instead, they shape the way you think while writing every line of code. And this is the big picture of system design. From the highest level architecture down to the smallest coding principles. System architecture decides how the entire system is deployed and scaled. Architectural patterns organize the structure inside the application. Design patterns solve recurring engineering problems between components. And principles guide the mindset behind every line of code we write. Once you see the full picture, every future topic suddenly connects together. We are not choosing Monolith over MVC or over design patterns. MVC, design patterns, and principles work inside a monolith or microservices architecture. And every architecture comes with its own pros and cons. We simply choose the one that best fits our project needs, while still following good engineering practices, so that as the project grows, it remains easier to maintain, migrate, and scale later. And we'll definitely dive deeper into some of the important architectures and patterns in the future. So, subscribe if you're interested, and I'll see you in the next one.